Greetings. My name is David Wairimu, and I'll be taking you through my presentation. And I'm very humbled to be part of this conference. See how we can modernize the agri-food systems of our continent. And my presentation title is Hybrid Optimization of Coccidiosis Chicken Disease Prediction, Detection, and Prevention using deep learning frameworks. And through my presentation, we are going to get to interact more with the topic and see how this can be done and scaled up to other initiatives. Okay, so there's my profile. I'm a student, an undergraduate student, taking agricultural systems engineering in my fourth year, second semester, and I'm in Jomo Kenyatta University of Agriculture and Technology, which is based in Kenya. My research interest spans from artificial intelligence in agriculture, additive manufacturing, with a special interest in bio-based materials, sustainable energy systems, and robotics in agriculture. So this will be the outline of my presentation. We start the introduction, the problem statement through challenges, and I'll give some of the references that I used in my study. And coccidiosis is a great and it's an important or key interest disease, especially in my country, because it's characterized by rapid spread and reduced production. And we can see in the image where the chicken, they just idling around. I mean, they're just sleepy and they cannot feed. That's the reduction in production. And also it also leads to mass death because it's very, very, it spreads so fast to other birds. And these in the overall results to high treatment cost because the farmer has to find medication and also incurring losses from the death of birds. And for this, we early detection and diagnosis with a key reference on artificial intelligence and it offers a novel solution to this challenge as we are going to see in my presentation. And the current diagnosis techniques are mostly visual and sound-based, which involve someone observing and listening to the birds, which are time-consuming. And also you have to be there all the time, almost all the times, and it's labor-intensive. And of course, it's prone to inaccuracies because it's visual and it depends on the experience of the person who is observing, because most of the time the vets are not always around the places or the rural areas. Mostly they are not always there to confirm, and they are prone to inaccuracies. And as such, we need to develop an automatic diagnostic system that also does not only detect but also give medication to the birds so that they're able to be cautioned against the disease or the presence of the disease, which is in this case is coccidiosis. In my methodology, it cuts across artificial intelligence and embedded system, where I prepare the dataset from a public repository. I train the model and tuned it to give the best parameters, to give the best accuracy. And then because of the dynamics involved, we need to have the best model because as we are dealing with lives, and we selected the best model and deploy it in a edge device and did the testing. For the dataset, I obtained it from a public repository, which was a study conducted in Tanzania, and Tanzania is a neighboring country. And with that closeness or proximity, then the disease or the symptoms are more the same because they are that close proximity. And yeah, the data set was verified by veterinary medicine experts, and that's the images that we used for the study are true to type of the coccidiosis disease. And I leveraged on the power of convolution networks models because of their high accuracy and also they offer lightweight models that can be deployed in edge device, because edge devices do not have so much computational power, and that's we need to have lightweight models that are going to be accommodated. And I tried a couple of models, MobileNet V2, ResNet 50, Exception, and VGG19. And from these ones, which are mostly lightweight, I was able to select the best that yielded highest accuracy. And transfer learning, it's an approach where you use a pre-trained model of this convolutional network to in the presence that you don't have enough data for you, because artificial intelligence requires one to have a lot of data, and that transfer learning approach also helps to improve the accuracy because you're not training this model from scratch. And yeah, we're able to tune the hyperparameters so that you obtain the best accuracy of the model. Yes. And a deployment of is done in a Raspberry Pi 3 Model B, but can also be done in a latest version of Raspberry Pi, yeah, which also have high computation power. And to do this, you need a TensorFlow-like file that you obtain from the best model. It's a conversion process that you do while training the model, and that you validated that it has the best accuracy. Then you convert the model itself to a TensorFlow, which it's lightweight and can be deployed in a edge device. And to get the inferences or the image feed from the environment on the test environment, we needed a library that could help us to obtain the images. And OpenCV, which is Open Computer Vision Library, was so instrumental in capturing the images which were able to pass through to obtain through a webcam and pass them through a model for testing. Yeah. And these are the results that we obtained. VGG19 had an accuracy of 89.15 and a validation accuracy of 90.63. And through the accuracy increased, but we settled to one model that's net 50 that yielded the best or the highest accuracy, because we need, as this environment is dynamic, and this is the first phase in a computer, because in the end we have to deploy this system in a field or in a house. So we need as high accuracy as possible in the computer, so that as we walk to the field, we'll have at least the model will be able to cope with the dynamic environment. Yes, that's why we chose the best model. And these are the training graphs and accuracy and validation and the loss. And the green line, it's the fine-tuning. Fine-tuning is where you unfreeze the train. As I told you, it's transfer learning approach. And transfer learning, you in the first phase, you freeze the base model, but in case the accuracy is not as much, you have the option of unfreezing, now training the model as a whole, and that's called fine-tuning. And the green line shows the fine-tuning, and it's evident that upon fine-tuning, the accuracy increases, the accuracy of the model, and that's also came handy to help us to boost the accuracy as high as possible, because that's the main aim, to have as much accuracy as possible for the model to be competitive, and be sure as a farmer that your model is going to perform well when deployed in the farm. Here in this is the schematic of the whole system at this phase. At this scope, we obtain the image feed from the environment, or from the test environment. We pass them through a webcam to the Raspberry Pi. Here indicated 4B. Yeah, you could do it 4B, 3B, yeah, all of them. But as you use the latest models, the device become more faster, because the latest versions have high computation power. And then the Raspberry Pi, because it's also an edge device, you can connect to actuators, in which in this case is a pump, but you connect to a vaccine or medicine receiver, and which connects to a water point that you can use now the chickens to get the medication, upon which if the disease is detected. And the inferences will be passed through the Raspberry Pi, which will iterate through to see whether the they are the same as the coccidiosis. And in the instance that they are the same, it will actuate pump to release the medication. Yes. Yeah, and these were some trials that I was doing, testing it on a printed paper. The fecal images was the ones that we were using because they are one of the prime symptoms which you can use to identify the presence of the disease, which they represent a real case, our real life situation. I also have a webcam that I was using now to obtain the image or the live feed. And then we have the Raspberry Pi 3 here. And then the relay board, because you cannot connect a pump direct to a Raspberry Pi because of the high current demand. So you need to use a relay module to make the connection. And then, yeah, the pump now to dispense the medication, the buds. Yeah, we're faced with different challenges and limitations, which include the different lighting positions as its camera-based system, but this can be improved by improving the lighting in the house. Also, the high cost of components, the Raspberry Pi, they are a bit expensive, and the biological systems are very dynamic. And in this case, the chicken environment, it's very dynamic. They may have the symptoms and the poop and all that, but because of the movements and all that, the inference can be tampered with by other chickens. So it's a very dynamic system. And yeah, with much studies and improvement, can be able to cope with this the dynamics involved in this environment. And these are some of the references that I used in my study, mostly intelligent systems and deep learning based references. Yes, and thank you so much for your attention. And I hope this presentation has opened eyes to how artificial intelligence can be leveraged to other areas. And the goodness with this system is that it can be scaled up to other diseases and other livestock and plant-based environments. And yeah, that's the most one of the key advantages of this, that you can be able to scale up because with enough data and computation power, you can be able to extend to other areas. Yes, and thank you so much.